we've arrived at momentum. The instantaneous momentum of an object of mass m is defined as the product of its mass and its velocity vector, giving a new vector, which we denote by the letter p momentum. And since it's a vector equation, it can be represented as independent equations for each of the components of the vectors. The x component of momentum is defined as mass times the x component of velocity, and so on. And furthermore, since it's a momentum equation, p and v would always be parallel to each other at every instant. Momentum and velocity, parallel vectors at every instant. Unit-wise, we've already shown that momentum has the same dimensions as impulse, which we measured in Newton seconds. So Newton seconds, or based on this, we can see that the combination of SI units, kilograms times meters per second, also gives us a unit for momentum. So these turn out to be equivalent, so we can measure momentum in Newton seconds or kilogram meters per second. Incidentally, why the letter P for momentum? Well, an older term for momentum that comes from the Latin is impetus. And that P there in impetus eventually became the P that we commonly use to represent momentum. So momentum used to be called impetus, and that pet there in impetus, that little Latin root there, that's the same pet as in centripetal or petition. It means to seek or to go towards. So impetus meaning we're going towards, moving in the direction of. That's our momentum. Just like centripetal means center seeking, pet seeking. Here we're seeking, going in the direction of going in some direction. That's our momentum. Alternatively, it's sometimes been suggested that the P is actually there for an alternate spelling of momentum, in which there's a silent P at the beginning of the word. I've heard that as well. All right, let's now re-express Newton's second law of motion in terms of this quantity, momentum. So starting with P equals mv for some object, let's take the time derivative of this equation, assuming that the mass of the object stays constant. So dp dt equals m, which is constant, times dv dt. And looking here, dv dt, that is acceleration. And acceleration is equal to net force over mass. So we can replace dv dt with net force over mass. So we're using Newton's second law here. And doing so, we see that we've got a mass and a mass that will cancel, leaving net force. So we've used Newton's second law to show that the net force, the instantaneous net force acting on an object, is equal to the instantaneous rate of change of the object's momentum. And this, in fact, is the original way of expressing Newton's second law. This is how Newton himself expressed his equation in terms of momentum. That was the more fundamental quantity to Newton than acceleration. So Newton wouldn't have written it this way. Newton would have written it this way. And again, what it's saying, expressed like this, is that the instantaneous net force acting on an object gives the instantaneous rate of change of the object's momentum. Here is net force changing the momentum of an object at each instant. So it's a new way of thinking about what interactions are. When objects interact with each other, the strength of the interaction, which we represent by the magnitude of the force, the strength of the interaction determines the rate at which the momentum of the object changes due to that interaction. So interactions change the momenta of objects. Oh, this is also a vector equation. So of course, when we use it, we usually represent it as separate equations for each component. So the rate of change of the x component of momentum is determined by the x component of the instantaneous net force, and so on. One more way of kind of rearranging this. would be to note that since the average net force acting on an object over some time interval is defined as in this time integral over the time interval, and we know this time integral is equal to our net impulse, and our net impulse by our impulse momentum theorem is equal to the change in momentum. What we're showing here is that the average net force on an object over some time interval equals the change in momentum over that time interval dividing by the change in time. This is one more instance of how you can take a derivative relationship and replace it with an average value relationship by replacing the d's with deltas. So F average becomes delta P over delta T. That's what we've got right here. And multiplying both sides of this by delta T gets us to here. Delta P equals the average net force times delta T, which is often just a handy way to compute changes in momentum. So the change in the x component of momentum would be equal to the x component of the average net force over that time interval times that time interval. And we see here that net impulse points in the same direction as changed momentum, delta P. These two vectors point in the same direction, which point in the same direction as average net force, which by Newton's second law points in the same direction as average acceleration. So all four of those vectors would be parallel to each other over any time interval.